So now we have to discuss about the position of the ESR absorption. Okay, that I will discuss. That is, due to the screening effects suffered by the unpaired electron in a molecular species, in an actual molecular species, the magnetic field suffered by the unpaired electron is not B0, but it is different from B0, that is B, because of the screening effects of other electron present in the system. Okay, or it is because of the screening constant. Okay, so we have the actual molecular species, an actual molecular species. In actual molecular species, the magnetic field suffered by the unpaired electron is not B0 but B. Therefore, now the equation reduced to, that is, nu is equal to GE beta B, where by H, where B is equal to B0 into 1 minus sigma, where sigma is called screening constant. It's called a screening constant. These things you have to remember. That is, in an actual molecule, the real magnetic field suffered by the unpaired electron is not B0, but it is B, that is equal to B0 into 1 minus sigma, where sigma is called screening constant, that is screening arises from the other electrons present in the system. Thus, we have the equation nu bar is equal to G0 B into B by H, that is equal to G beta into B0 into 1 minus sigma, that is equal to G beta B0 minus G beta B0 sigma, that is equal to G beta B0 into 1 minus sigma, and the term G into 1 minus sigma, that is G into 1 minus sigma can be taken as G, the G factor, or the real unpaired electron in the molecular system. Therefore, that is equal to G into 1 minus sigma can be replaced by G. Therefore, the equation now becomes G into beta into B0. Beta into B0. So, our equation now become by H. Now, our equation now become like this. That is, nu bar in the frequency of the radiation at which the ESR absorption takes place, nu bar is equal to G beta B0 by H, where G is equal to G into 1 minus sigma, where G is called that is electron G factor of the electron in an actual molecule, which should be different from the free electron. We should be different from the G value of the free electron. Then only we can identify the molecular species. Okay, I have represented. So the position, it is more convenient to consider. So this is called G value. It is we have seen that this equation shows that according to this equation, we have to remember is that this equation shows that nu, the frequency, the radiation at which the micro radiation at which the ESR absorption takes place is directly proportional to B0, directly proportional to the applied magnetic field. Therefore, but we have to work with a particular range of magnetic field for an ESR work. So it is more convenient to represent the absorption line or absorption frequency in terms of the G value. So it is more convenient to consider the absorption in terms of the G value. And I have already mentioned, for a free electron, the G value at which absorption takes place is 2.0023. So the G value for a free electron at which absorption takes place is, okay. So in an ESR spectrum, the absorption frequency is represented in terms of the G value. So, okay, the absorption frequency is represented, absorption line is represented, each node corresponds to a particular absorption line, and this position of the absorption line is represented by means of the G value. For a free electron, the G value representing the absorption line is equal to a value this 2.0023 depending, and for all other electron in a real molecular species, for all other electron in an actual molecular species, they have a G value different from this 2.0023 depending on the screening constant. So in all other, for free electron, the absorption position of the absorption frequency is represented in terms, it is more conveniently represented in terms of the G value of the molecular species, G value of the electron present in the molecular system. For a free electron, the G value is 2.0023, which represents the absorption position of free electron. For all other electron in a real molecular species, its G value is different from this 2.0023, okay, depending on the screening constant. Okay, the G factor is sometimes referred to as, so that thing, the G factor in ESR is sometimes referred as the counterpart of chemical shift delta in NMR. Okay, it is better to consider the G factor in an ESR can be considered as a counterpart of, analogous to, it's a counterpart of the chemical shift delta in NMR. But some difficulty is there. That is, here in the ESR spectrum, the variation observed in the G factor from compound to compound is not as significant as that of chemical shift delta. Okay, NMR delta compound to compound variation polar significance നമ്മുടെ ESRന്റെ G value കാണുന്നില്ല. That's the difficulty. Okay, the variation observed in the G value from compound to compound from this value, okay, from standard value 2.0023, okay, that variation observed in the G value from compound to compound is not much significant as that found in the NMR delta shift. For most organic free radical, the G value is close to the G value of the free electron. That's the difficulty. For most organic free radicals, the G value of the actual electron is close to the G value of the free electron. That is, it is very close, and it is only very small value. It is close to this value, having a variation of plus or minus 0.003. So, for actual electron, the variation in the G value of most of organic free radical comes to be nearly plus or minus 0.003 only. So such a small variation is only from compound to compound from this standard value. That is the difficulty in distinguishing between any other free radical from one another, and also to compare it from the free electron G value. The reason is that the unpaired electron in most of the free radical behaves just like an electron in the free space. It is a delocalized system. The unpaired electron present in the most of the organic free radical behaves like a delocalized system. So it behaves like an electron present in a free space. Okay, that is why most of the free radicals from compound to compound radical, the values differ very much, very small, very small, very close together, and it is 0.003 difference plus or minus from also from this value. So we have to find a difficulty in analyzing the other radical from the free electron or from one compound to another. The organic free radical തമ്മിൽ കണ്ടുപിടിക്കാനായിട്ട് ബുദ്ധിമുട്ട്. There is a kind of overlapping. Okay, so when we going to take the absorption spectrum, okay, the difficulty is like there is a kind of overlapping occasion here. That is calculation is very find to be difficult. On the other hand, in ionic crystal, okay, certain paramagnetic ionic crystal, that is paramagnetic transition metal ion, the electron is localized in a particular orbital. Okay, there occurs a coupling between the spin angular momentum and orbital momentum, and as a result, the G can differ considerably from that GE. ഈ വാല്യൂന് വളരെ വ്യത്യസ്തമായിട്ട് ആ കോമ്പൗണ്ടുകളിൽ നമുക്ക് ഉണ്ടാകുന്നുണ്ട്. So we found the difficulty in the case of organic free radical, okay, because of the closer value. Suppose on the other hand, in the ionic crystal, that is the paramagnetic transition metal ion, the electron is localized. The electron is localized in a particular metal orbital about the atom, and there occurs a coupling between the spin angular momenta S and orbital angular momenta. Okay, as a result of S and L coupling or orbit coupling, okay, or coupling interaction, there occurs a considerable difference in the electron present in such system. Therefore, the G value from the G value, and the value can vary from 0.2 to 8 have been reported. Okay, 0.2 നും 8 വരെയുള്ള value report ചെയ്യുന്നുണ്ട്, a variation than considering with the free electron in space. So let's try to consider the ESR spectrum and representation and the standard. അത്രയും കൂടെ കാര്യങ്ങൾ ഡിസ്കസ് ചെയ്യേണ്ടത്. So we discuss the ESR spectrum is representation and the standard you have to select. Any paramagnetic sample in the form of a single crystal or in the form of a powder or in the form of a liquid or in the form of a solution can be used for the analysis with respect to microwave radiation under the magnetic field. So in the ESR spectroscopy, we can use the paramagnetic species in any form, either in the form of a single crystal or in the form of a powdered form or in the form of a liquid form or in the form of a solution. Okay, and it is radiated with the microwave radiation of suitable frequency or constant frequency under an applied magnetic field. Then the transition occurs. The transition occurs from one spin level to the other spin level due to the absorption of energy from the microwave radiation, and this absorption lead to this transition which create a spin flip. So when the paramagnetic sample is radiated with the microwave radiation under the influence of the magnetic field, due to the transition of the molecular species from lower spin level to the higher spin level, or due to the transition between the electronic spin level by the absorption of the energy from the microwave radiation, there occurs a spin flick there occurs an electron spin flick, the absorption of the microwave radiation, causing the transition from between the two electron spin level produces an electron spin flick, and the electron spin corresponding to the electron spin flick, there is an absorption line. Okay, there is a change in intensity or the transmitted microwave and which produces an absorption corresponding to a particular frequency having a peak. That is the representation. So, that is, each absorption causing an electron spin split, and the detector receives a transmitted microwave and decreasing intensity and produce an absorption line on the charge at a particular frequency. An ESR spectrum can be represented suitably by plotting. Okay, how do you represent? Oro spin transition, electronic spin transition of the molecule, electronic spin transition by the absorption of a particular microwave frequency which produces a signal. Okay, electron spin flip corresponding at absorption line. That is, in the ESR spectrum, it can be represented by plotting the intensity of the signal, against the applied magnetic field. So normally, these are methods. The intensity of the signal. This is the signal S. The signal S, intensity of the signal S is plotted against B0. So corresponding to the maximum absorption of a particular frequency of the microwave. Okay, this is the signal intensity of the microwave signal. So corresponding to absorption of occurs at a particular frequency, we have a peak in the signal. So normally in the ESR spectrum is can be represented by plotting the intensity of the signal. Intensity of the signal, yes, against the applied magnetic field B0, and corresponding to the absorption, we have a peak. The peak may not be, it is usually a broad peak, okay. The broad is usually a broad peak. That is a difficulty in analyzing this. In order to avoid the consideration or there is confusion, since the peak is not actually not strictly peak, it is a broadened peak. It is better to modify this plot. So instead of deriving the modern ESR spectra, it is a derivative curve is obtained. That is, instead of plotting the signal intensity against the B0, here the first derivative of the signal intensity, that is with respect to B0, ds by dB0 is plotted against B0. So in actual cases, instead of the intensity of the signal, the first derivative of the signal intensity ds by dB0 is dB is then plotted against B0. ds by dB is plotted against B0, so that corresponding to the peak, it will cross the abscissa, producing a maxima and a minimum. That's something. So ds by dP with the value, this negative and this positive, we have like this. So corresponding to this, the curve has a maxima and minimum. It's the typical curve. Okay. The maxima, when we, in the case of actually ESR spectroscopy, the first derivative of the signal intensity is plotted against B0, that is ds by dB is plotted against B0 rather than S versus B0. So that the peak of the absorption curve S bar B is now correspond to, it will crosses the abscissa. Okay, it will cross the abscissa from a maximum to minimum. From maximum minimum peak in peak. So when we plot the ds by dB against B0, the first derivative of the signal intensity against the applied magnetic field, the signal obtained is like this. That is, the peak then passes through crosses the abscissa, and the number of peak now here correspond to the number of maxima and the minimum. That means one peak, a signal with the one peak now produces a maxima, one maxima and one minima, with the peak now crosses the abscissa. So in the derivative curve, the number of peak in the absorption curve now become equal to the number of maxima and minima, with the peak now crosses the abscissa. ഇതാണ് മനസ്സിലാക്കേണ്ടത്. ഡെറിവേറ്റീവ് കർവിൽ നമ്മൾ ശ്രദ്ധിക്കേണ്ടത് ഒരു അബ്സോർപ്ഷൻ പീക്ക് എന്ന് പറയുമ്പോൾ ഒരു മാക്സിമയും ഒരു മിനിമയും ഉള്ള രണ്ട് പീക്കായിട്ടാണ് വീഴുന്നത്. അവിടുത്തെ പീക്ക് ഇവിടെ abscissa കൂടി ക്രോസ് ചെയ്യും. So there are as many number of maxima and minima corresponding a particular peak in an ESR spectrum. So that we are doing. Then here the peak height has no significance. Each absorption peak now correspond to a maxima and minimum, with the peak now stands in the abscissa, across the abscissa. Okay, so there are as many number of maxima and minima as the number of peak in a ESR spectrum. And the information from the ESR spectra, the height of the peak has no significance, but the total area under the peak, okay, the total area under the absorption peak or this type of derivative peak, the total area, both the total area under the peak is proportional to the number of unpaired electrons present in the sample. That's very important. The peak height has no significance in the ESR spectroscopy. Instead, the area under the peak, both absorption curve or in the derivative curve, the area under the peak represent the total number of electrons present per gram of the sample. That is, the number of unpaired electrons in an unknown sample per gram. It represents the total area of the peak represent the total number of unpaired electrons present per gram of the unknown sample. And it can be obtained easily by comparing it with a curve or standard having known number of unpaired electrons per gram. That's the technique. So the number of unpaired electrons in an unknown sample under the area of a particular ESR peak can be obtained by comparison with a standard curve whose number of unpaired electron under its area is per gram is known. Okay, so we have to select a standard compound having a known number of unpaired electron per gram of the material. As such a material selected is the most commonly used standard in ESR work is the standard. The most commonly used standard in ESR work, ESR spectroscopic work is, that is diphenyl, okay, picryl, diphenyl picryl hydrazine radical. So this is a standard compound use, that is paramagnetic compound use, that is diphenyl picryl hydrazine radical. Diphenyl, DP, then picryl hydrazine, DPPH is the abbreviation, DPPH, diphenyl picryl hydrazine radical, is a standard used in ESR spectra. Okay, It contains 1.53 into 10 to the power of 21 unpaired electron. So the signal of this compound contain, okay, the area under the curve of such a signal of this compound contains 1.53 into 10 raised to 21 unpaired electron per gram. This was important. So diphenyl picryl hydroxyl radical, that is called DPPH, is the standard used in the ESR spectroscopy. Is also considered as a counterpart of that is, okay, in the NMR. Okay, NMR നമുക്ക് ഒരു counterpart ഉണ്ട്. Okay, അതിന് പോലെ തന്നെയാണ് ഇവിടെ DPPH. അവിടെ ഏതാണ്? ടെട്രാ ഇഥൈൽ ഓക്കെ TEH. ഓക്കെ, ആ കോമ്പൗണ്ട് എനിക്ക് നോക്കണത് ടൈം ചെയ്യാതെ ഞാൻ മറന്നുപോയി. ദാറ്റ് ഈസ് CH3 4 times. Okay, let tetraethyl, let tetraethyl. So this diphenyl picryl hydroxyl radical is called DPPH is considered as let tetramethyl. Okay, let tetramethyl, let tetramethyl TML, I think. Tetramethyl lead in the counterpart ആണ് ഏത് DPPH എന്ന് ഓർത്തിരിക്കുക. So what I want to mention is that the area under the curve is significant, which represents the total number of unpaired electrons present in an unknown sample, okay, per gram of the sample. And it can be easily found out by comparing it with a standard signal containing a known number of unpaired electrons. That is the standard usually taken is diphenyl picryl hydroxyl radical, which contains 1.53 into 10 raised to 21 unpaired electron per gram of the material. Okay. So by comparing, and that is when applying, and it has a very strong detectable limits. Okay, DPPH contain 1.53 into 10 raised to 21 unpaired electron per gram of the material, and with the normal ESR with a having a detectable limit of less than 10 raised to minus 9 gram. That is very powerful. Even it has a detectable limit of 10 raised to minus 9 gram. So with the using normal ESR, we can detect up to a very small quantity of 10 raised to minus 9 gram, minus gram. Then also it has a G value close to 2.0026. Yeah. ഈ കോമ്പൗണ്ട് പ്രത്യേകതാണ് 10 raised to minus 9 ഗ്രാമിന്റെ റേഞ്ചിൽ ലിമിറ്റിൽ പോലും ഇതിനെ നമുക്ക് ഡിറ്റക്ട് ചെയ്യാം. And also it has a G value for 2.0026. Thus we can find out the number of unpaired electron from the signal of any unknown compound. Okay, with the paramagnetic compound. That's a big one. Then again you have to remember the problem is that since the G value of most of the compounds, not 26 but 36. The G value is 2.0036. Free electron 2.0036. Since G value of most of the radicals are very close to this, DPPH cannot be used as such. Either simultaneous at the okay. Since most of the organic free radical has a G value closer to this 2.0036 ആയതുകൊണ്ട് DPPH cannot be used for measurements along with the sample. Sample കൂടെ തന്നെ നമുക്ക് അതിന് ഉപയോഗിക്കത്തില്ല. അതിന് പകരം because overlapping ഉണ്ട്. I not avoid overlapping line. Its spectrum is recorded separately. The spectrum of the standard is taken separately from the spectrum of the unknown sample. That is a technique that you have. In order to avoid the overlapping signal, the unknown sample and DPPH signals are taken separately in a particular record. Okay, a particular record, given record, separate the signal light in order to avoid overlapping because of this thing. The G value of most of the radical is very close to this value. So the sample is not exposed along with simultaneous with the DPPH. Instead, the signal of DPPH and sample are taken separately in a given recorder. Otherwise, okay, but scanner, two separate scanners in order to avoid overlapping, is the scanning is not taken simultaneously. A single scan is not used for producing the signal. So they are recorded. The scanning is carried out separately, independently to avoid overlapping. I hope that you have followed. Then otherwise, a trace of chromium-3 entrapped in tiny chips of ruby crystal and cemented permanently to the sample cell can be used as an internal study. Chromium poലുള്ള unpaired electron metal ion, because the strong LS coupling, the unpaired electron are localized to the orbital around chromium. Therefore, they can produce a G value. Okay, because the strong signal, its G value 1.4 can be very well distinguished from other free radical. So the other standard that can be used is chromium-3. Chromium-3 cemented entrapped in a tiny chip of ruby crystal. A trace of chromium-3 is trapped in a tiny crystal or ruby crystal, tiny chip of ruby crystal, and is then cemented permanently to the sample hot cell. Sample cell permanent ruby crystal chip chromium-3. Okay, chromium-3 with unpaired electron species. Permanent cement. Because this species, chromium-3 species, has a very strong absorption signal, which is different from that of any other free radicals, and this has an absorption peak with the G value 1.4. 1.4 and G value is the Let's try it. Okay. It has an absorption peak, that is C chromium-3 has an absorption peak with a G value 1.4. The G value 1.4, that is different from, distinguished well from all other free radicals. Scan separated main DPPH common one problem sensitivity under -9 gram sample and it has a G value 2.0036. That is the problem. Most of the radicals are G value close to this. Therefore, to avoid the overlapping of the signal, scanning is carried out separately. Okay, sample and the DPPH is recorded in a ESR instrument in a separate scan and then compare. Otherwise, we have to take another standard, that is a chromium-3 trapped in a ruby crystal, a chip of ruby crystal, and is placed permanently to the sample holder. That can have a very well distinguishable G value different from any other radical, that is G value is 1.4. So, that is the thing. In the next class, we have to discuss the important aspect in the ESR spectra. Okay, ESR is the hyperfine splitting. The actual spectrum, how we can view the actual ESR spectrum, the ESR spectrum of a real molecule. Okay, so this is a molecule containing unpaired electron is in the neighborhood of a nucleus with a resultant spin. Okay, what happens? Suppose the unpaired electron is in the neighborhood of a molecular species in which the nucleus is also possesses a resultant spin. What happened to the signal? Okay, that is called hyperfine splitting. Hyperfine splitting, which follows quantum mechanical selection rule. Okay, that is called a electron spin interact with the nuclear spin. The electron spin, yes, going to interact with the nuclear spin I, or M must interact with the Mi. The electronic spin M must interact with the nuclear spin Mi, thereby cause the splitting of the line further. For further splitting of the line, that is called a hyperfine splitting. And that is to be governed by two quantum mechanical selection, one for delta Ms and other for delta Mi. So this aspect can be discussed in the other class. Okay, thank you very much.